araw, no? At least dito sa amin. Kaya Meralco Bill is waving. Pero anyway. Okay, so good morning, everyone. So today we'll talk about module number 8, which is Initiative pa. I just finished it right before midnight yesterday. So grab a copy, pero advance notice, this will just be for today. Hindi ko pa natatapos isulat yung para sa Friday. But I think that will be lighter because we will only discuss 2 more methods after that. But basically, module number 8 is focused on developing some iterative techniques in solving linear systems. So parang katulad to nung ginawa natin sa root finding na, kasi sa root finding wala tayong direct way. So kailangan mag-rely talaga tayo sa mga iterative or interval schemes wherein we are getting a sequence of approximates for the roots of our function. Yung diniscuss natin sa module 7 ay direct methods. They are quite deterministic. Direct sila kasi kapag pinerform natin lahat ng calculations by hand, we will get an exact solution. Of course, with the appropriate assumptions on the matrix A or the coefficient matrix A. And then they are deterministic because there is a predetermined number of operations that needs to be done in order to get the solution. All right. So sabi natin, yung sa Gaussian elimination, big O of n cubed, number of operations yung kailangan nating i-perform. So if you go short of that total number of operations, hindi matatapos yung algorithm, wala kang makukuhang estimate. So by hook or by crook, we need to carry out all of those operations in order to get a solution, right? So which is not ideal for most cases, right? So yun titingnan natin sa module number 8. Now, parating pa lang tayo sa exciting na part ng course, all right? Pero ito yung bad part. I think we will finish unit number 2 next week. And that's the bad part for you because that means I need to give you the second problem set. Pwede ko na siyang ibigay actually next week para maging due siya week after next. But the bad thing is kasabay siya ng 155. And I think most of you are taking 155 right now. So ano kaya yung magandang remedyo? Or maliit na bagay lang ba yun at kaya nyo nang gawin yun? Napagsabayan. Let me... Actually, pinag-iisipan ko pa rin. Do you guys have any suggestion? Or is it okay if we delay the problem set 1 week? So instead na ibigay ko siya next week, ibigay ko siya week after next, and it will be due 2 weeks from next week. Para lang hindi makasabay ng mga nag-155 yung problem set natin. Okay lang ba 'yon? Kaya lang medyo lalayo kasi medyo nagdi-discuss na tayo ng unit 3, then that's the time that you will be doing problem set 1. But yeah, it's a scheduling nightmare for me. So yeah, I'll think more about it. Then if you have some suggestions, let me know. Pero kung kaya niyo naman pagsabayan, sabihin niyo lang din so willing din naman akong pagsabayan sila. Pero mukhang hindi siya ideal. All right? So let's put a pin on that. Okay, so right. Kasi sanay na naman kayo sa mga ganung galawan na halos sabay-sabay yung mga courses. Napapagsabay nyo nga yung 175 at saka yung course nyo sa ibang teachers tapos yung sa akin ayaw nyo pang pagsabayan Bigla na konsensya. Pero anyway, so let me think about that and rest assured that I'll take into consideration the best for you guys, okay? So, going back to our topic. So, yung mga methods na diniscuss natin last time, yung factorization methods, they are direct and they are deterministic. However, minsan may mga matrices kasi na hindi kailangan nating i-perform yung ganong karaming operations just to get a nice estimate for our solution. All right? Especially yung mga tinatawag natin halimbawa mga sparse matrix. Yung mga sparse matrix, sila yung mga matrices na maraming zeros yung entries nila. Okay? And this type of matrices always pops up in applications. So, madalas, halimbawa sa modeling ng paano nagva-vibrate ang isang spring mass system or paano paano nagbe-behave ang waves. So kaya mo siyang isulat na kaya mo siyang i-model using a linear system na napakaraming zeros ng matrix na yon. And if you have a matrix with lots of zeros, for instance, may mga methods na hindi mo kailangan mag-perform ng big O of n cubed number of operations, which will be required kung yun yung gagawin natin dun, kung gagamitin natin yung Gaussian elimination o yung mga LU factorization schemes, right? Kasi nga, by hook or by crook, kailangan nating i-perform lahat ng operations na yan para makakome up ng exact or nearly exact solution. Now, kung may magandang structure yung matrix mo, halimbawa siya ay sparse, halimbawa siya ay tri-diagonal. When we say tri-diagonal, ang may non-zero entries lang yung main at saka yung first upper and lower diagonal entries. Mas madali siyang isolve. And the Gaussian elimination techniques will be an overkill to get an estimate for those methods, right? So yun yung gagawin natin sa module number 8. We will look at some iterative schemes for solving linear systems. Uh, Kasi itong mga iterative schemes na to, non-deterministic itong mga to eh. There is no guarantee that we know beforehand how many operations should be performed in order to get a good enough estimate, right? Katulad nung halimbawa bisection, regular falsi, Newton-Raphson, fixed point iterations. Nagde-decide tayo on the fly or when we are actually implementing the algorithm kung okay na ba yung nakuha nating estimate. If we're happy with the estimate that we already have, then ititigil na natin yung operations. Tinitigil natin siya. So it's more of a non-deterministic approach. Kasi nga, nakadepende dun sa sequence of estimates na nakukuha natin kung ilang operations yung kailangan nating gamitin. And it is actually sometimes, I think this is something new because we were always taught to use direct methods pag solve ng linear systems, right? But if you think of it, kung nagagawa natin siya sa mga nonlinear equations, there could be a natural extension to do those techniques insofar as linear systems are concerned. Medyo tricky nga lang yung linear systems kasi simultaneous yung equations. Simultaneous meaning dapat yung lahat ng equations na nandun sa system, sabay-sabay silang nag-hold. Right? So yun titingnan natin. Paano natin posibleng ma-extend yung mga iterative schemes na na-discuss natin for root finding into linear systems. Although mas komplikado to kasi simultaneous nga dapat nangyayari yung mga equations, alright? But the nice thing about this is linear lang yung bawat equations. Yun nga lang, linear sila pero maraming variables na involved. Right? So for this week, I'll teach you 3 basic iterative schemes. They're called the Jacobi method, the Gauss-Seidel method, and the SOR method. Okay. Marami pang iterative methods, but to make complete sense of how they work, I need a lot of linear algebra stuff. So kaya medyo limitado ako dun sa mga simpleng method para i-discuss sa inyo. But hopefully, after you went through your junior year nyo nga ba kinukuha yung linear algebra 174, 175. So when you go to your senior year and you came across, say, a linear system that you need to solve sa inyong SP or thesis, tas hindi siya kaya ng mga na-discuss natin sa 175, then with the learnings that you get from 175, yung training na nakuha nyo, hopefully, mula dito sa ating course, and the knowledge from 120 or 105, kaya nyong pag-aralan yung iba pang iterative schemes para sa linear systems. Okay? Now, our objectives is to compute some matrix and vector norms because kailangan natin ng measure kung kailan tayo titigil sa iterative schemes, right? And I'm not sure if you have met these norms or these measures for matrices and vectors. So in-insert ko siya sa preliminary thing for module number 8. And then after we discussed some matrix and vector norms, I will introduce you the Jacobi method. And then yung Gauss-Seidel at SOR methods gagawin natin sa Friday. Typo ito, dapat. And then, of course, the ultimate goal is to use these iterative methods to solve scientific problems. Content, ayan, handwritten na uli yung module. Sabihan nyo lang ako kapag hindi nyo mabasa yung sulat ko. Ano? So, umpisa natin sa vector norms. So, usually, Vectors in general, ito ay elements ng isang vector space. And if you have taken linear algebra courses, then you might have realized na ang vector spaces ay hindi lang mga one-dimensional matrix. All right, so basta meron siyang properties na nasa-satisfy vector spaces sila. At lahat ng elements ng isang vector space, arbitrary man yan, abstract man yan, ang tawag sa kanila ay vectors. And then most of the things that we'll discuss here can also be extended to those abstract vectors. But for our discussion, I will just consider or I will just use vectors to pertain to n by 1 or 1 by n matrices over a field. All right? Pero yung field natin gagamitin ay either set of real numbers or complex numbers lamang. So when I say vector, siya lamang ay isang n by 1 o isang 1 by n matrix na ang laman niya ay mga real numbers or complex numbers. Okay? Then we define what a vector norm is in definition 8.1. So yung function na to, yung parang norm bar or double absolute value bars, right? It's a function that takes a vector r to the n, okay? So, nabanggit ko na nga ba dito? Kapag ka meron kang n by 1 o 1 by n matrix, susulat na lang natin siya as f to the n. Yan pala. Alright, so kung Rn, pag sinulat ko na Rn, ibig sabihin yan ay set of all m by 1 matrices o set of 1 by n matrices na ang laman niya ay puro real number. So kukuha lang ako ng isang vector, tapos nag-assign ako sa bawat vector ng isang positive real number. Tapos ano yung property? Kasi itong norm na to, ito yung parang magiging measure na gaano kalaki yung vector natin. Okay? Now, in order for a function that maps a vector into a real number to be a norm, dapat masatisfy niya itong mga sumusunod na bagay. The first is the non-negativity assumption. Dapat laging non-negative yung norm ng isang vector, which makes sense because this is a measure. So gusto natin laging positive, laging non-negative yung measure natin. Property number 2, this is the zero property. That means the norm of a vector should be equal to 0 if and only if x is the zero vector. Pangatlo is the homogeneity property. Homogeneous dapat yung function para maging norm in such a way that the magnitude of a scalar or the norm of a scalar times a vector is equal to the absolute value of the scalar times the norm of the vector. So parang yung isang scalar multiplier sa isang vector ay nagiging scaling factor lamang nung kanyang norm. So parang siya yung amplifier lang, parang amplifier lang siya nung size nung vector. Okay? And then the fourth one is your good old triangle inequality. The norm of a sum is no greater than the sum of the norms. Okay? So generalized triangle inequality lang yan. So kung meron kang isang function that maps a vector into a real number satisfying these four properties, then that measure is called a vector norm. Okay. Everything here holds if you replace r to the power n by the set of complex numbers. All right. So okay pa rin siya. And actually, you have seen an example of a vector norm. If n is equal to 1, then you will have a norm defined on the set of real numbers. And the natural norm there is simply the absolute value. So isang madaling example ng isang norm or isang vector norm ay ang absolute value function at ito ay isang norm from r to the 1 papunta kay r. Another thing is the modulus function, yung absolute value o yung modulus ng isang complex number defined as halimbawa si z ay complex number na equal kay a plus bi. Ang kanyang absolute value ay a squared plus b squared taken the square root of. So isa rin siyang norm. So ito yung mga usual norm na na-meet nyo before. Okay? Magpapakilala lang ako ng ibang mga norms. Pero specifically, ito ay mga norms kay r to the power n. Okay, so vector space. And usually this is taken when n is greater than 1. Pero nag-work din to kapag kasi n is equal to 1. Pero ang gusto nating tingnan ngayon, yung mga mas malalaking dimension. Tama? So una sa example 8.1, ito yung tinatawag natin na Euclidean norm. Okay? Tapos to denote it, naglalagay lang tayo ng usual norm bar, tapos may subscript na 2. So how do we compute the L2 norm or the Euclidean norm of a vector? Kung yung vector natin, ang entries niya ay x1, x2 until xn, then the 2 norm or the L2 norm or the Euclidean norm of the vector x is just the square root of the sum of the squares of the absolute values of the entries of x. Okay? So, pero familiar naman kayo dito, no? Ito yung length ng vector x, the usual length that you met in math 38. Okay? So, kunin niyo yung absolute value ng lahat ng entries, square niyo silang lahat, tapos kunin mo yung sum, tapos i-square root mo, yun yung measure ng L2 norm ng vector natin. Okay? And then in general, you can define the P norm, where P is actually a number from 1 to infinity. All right. Usually we take this to be what? We take this to be integers, but actually there's no restriction for them. Basta greater than 1, greater than or equal to 1, okay siya na norm. Okay? Pero paano natin siya kino-compute? The P norm of a vector x is just the pth root or kunin mo yung sum ng absolute value raised to the power p ng bawat entry. Pag nakuha mo na yung sum, kunin mo yung erase mo siya sa 1 to the erase mo siya sa 1 to erase mo siya sa 1 over p. All right? So yun yung ibibigay niya sa iyo na p norm. Okay? So you can replace p by any number greater than 1 or greater than or equal to 1, then you'll get a norm. Tapos ano pa ba dito? Then we have the L infinity norm. Yung L infinity norm naman ay de-denote natin by the norm bars, may subscript na infinity, tapos it is computed as the maximum absolute value among the entries. Okay? Makikita mo lahat ng entries, kunin mo yung absolute value nila, yung pinakamalaki, yun yung i-assign natin as the L infinity norm of the vector x. Okay? And usually, yung infinity norm, sinasama natin siya dun sa class ng mga p-norms. Okay? So, usually ito ay treated as a p-norm with p equals infinity. Alright? So, sa mga texts, pag sinabing LP norm or sinabing p-norm, kadalasan kasama dun sa discussion yung infinity norm. Okay? Now, ito yung mga usual na pinipili natin to measure how big a vector is. Alright? So, pili kayo dyan kung ano yung gagamitin natin. Of course, there are some other norms. Hindi ko na lang siya inilagay dito. Pero ito yung mga of particular interest for us. Okay? Just to give you an idea how they are computed. Okay? So, tingnan natin yung example 8.3. So, nagbigay ako dyan ng isang vector, isang three-dimensional, isang 3 vector. So, it's 5, -1, 7. Okay, nakatranspose lang naman siya. So, assume ko to ay 3 by 1. Okay? Tapos, computein daw natin yung Euclidean norm, the 1 norm, the 4 norm, and the L infinity norm. Okay? Euclidean norm. Square root ng sum ng squares ng absolute values. So, take the absolute value squared. So, we'll get 5 squared, -1 squared, 7 squared. Simplify that, you get 5 root 3 or 8.66. Okay? Tapos yung 1 norm naman, gamitin nyo lang yung definition ng P norm when P is equal to 1. So magkakaroon siya ng first root, which is just essentially the sum itself, summation ng absolute values. So 5 plus absolute value of -1 plus 7, you get 13. Okay? The 1 norm is usually called the taxicab or the Manhattan norm. Hindi ko pala siya na-note doon para meron tayong mas ibang tawag sa kanya. Okay? So, isa rin siya sa mga usual norms na kinukuha. Madali siyang i-compute kasi bibigay niya lang sa ang L1 norm lang naman ay yung sum ng mga absolute values ng mga entries. Okay? Tapos yung 4 norm, of course, I'll just use P equals 4 dun sa formula natin kanina. So I'll get the fourth root ng sum ng fourth powers ng mga absolute values. Okay? So this doing that for the vector that we have, we'll get the fourth root of 3000. And then finally, we compute the L infinity norm of the vector x. The L infinity norm is just the maximum absolute value among the entries. So here, this will have absolute value 5, absolute value 1, absolute value 7. The biggest is 7. So that's our L infinity norm. Okay? So ito yung mga usual ways ng pagko-compute natin gaano kalaki ang isang vector. And this will be important because when we are designing iterative schemes, we want to measure, di ba sa one dimension case, ang ginagawa natin ay mini-measure natin kung ano yung relative jump, for instance, all right? How big is the jump from the previous estimate to the new one? Ganun din yung gagawin natin sa iterative schemes ngayon. Kaya lang remember, ang estimates natin ngayon ay mga vectors. So gusto nating makita ano yung relative change from our vector right now from the next vector that we'll be getting. Alright? So kaya kukunin ko yung ratio ng gaano kalaki yung difference between the two estimate vectors all over the previous estimate vector. Kaya napilitan akong i-discuss itong mga vector norms sa inyo. And actually medyo relative yung measure ng ng isang um, isang vector because it depends on what type of norm you choose, all right? So kaya lang may magandang property yan, at least finite case. Nabura yung definition. So merong isang equivalence property, all right, sa mga norms sa finite dimensions. Kaya kahit anong norm yung piliin mo, hindi nagkakalayo-layo yung mga properties ng sequence of estimates na makukuha natin. All right? And actually not just that, kung if you're familiar with topology, since norms are or if you have equivalent norms, they will induce equivalent topologies, all right? So pare-parehas yung properties nila. Parang meron lang scaling factors yung isang norm from the other. But what do we mean exactly when we say equivalent norms? Yun yung nasa definition 8.2. We say that two norms defined on the same vector space are equivalent if and only if there exists positive constants C1 and C2 such that this inequality holds. Right? Na yung norm ng isang vector under the first under one of them. Halimbawa dun sa yung kanyang prime norm. Tawagin natin tong prime norm. Kung yung prime norm ni x ay bounded below by a multiple of the norm of x and another multiple of the norm of x, then we say that the norm and the prime norm are equivalent. So parang kaya mong i-sandwich yung isang norm between two scalar multiples of the other norm. So meron silang parang squeezing property. Kaya yun yung tinatawag natin na equivalent norms. And Theorem 8.1 is a classic result from linear algebra that tells us that all norms on a finite dimensional space are equivalent. So kaya free tayo to choose any of the norms that we have for vectors pag me-measure ng mga error. Kasi at the end of the day, lagi silang nagiging equivalent naman silang lahat. So if we have a good enough or a small enough error vector with respect to one of those norms, then that is also guaranteed to be a small enough with respect to another norm. Right? So hindi pwedeng malaki yung value, hindi pwedeng maliit yung L2 norm niya, pero napakalaki ng L infinity norm niya. So that cannot happen because of the equivalence property or equivalence property 8.1. All right? So for the proof savvy guys, I will not show any proof for this module kasi linear theoretic yung mga proofs na to. So they are properly discussed in linear algebra courses. Now, I hope nakita niyo yung importansya nung mga vector norms, okay? So sila ay para ma-measure natin yung errors, okay? Mahalaga rin yung matrix norms or how do we measure the size or the magnitude of a matrix insofar as convergence analysis is concerned. Makikita nyo mamaya kasi yung iterative schemes natin nakadepende sa isang matrix. All right? So kailangan nating malaman ano yung measure of magnitude para sa isang matrix kasi yun yung makakapagbigay sa atin ng idea kung kailan magko-converge yung ating iterative schemes. Right? Now, we define a matrix norm here in definition 8.3. So it's just a function from the set of all n by n matrices papunta kay R satisfying the following conditions. But you will notice that the first three and the fifth properties here are exact replicas nung properties na meron ang vector norms. Kasi after all, ang matrix, ang set of all matrices ay isa ring vector space. All right? Vector space nga, yeah, it's also a vector space. Kaya naman, magkamukhang-kamukha yung definition nila. So you have the non-negativity assumption here, the zero property here, the homogeneity property, all right? And here you have the triangle in, the fourth pala yung triangle inequality. So, sorry, let me correct that. The first four ay complete replicas na nandun sa definition 8.1. All right. The added condition here is the fifth property, which is the Cauchy-Schwarz inequality. So, Cauchy-Schwarz inequality that says that the norm of a product will not exceed the product of the norms. And this is also an important result for us para sa convergence analysis. Okay? So pag meron kang isang function that assigns a real number to a matrix that satisfies all these five properties, then that function is a matrix norm. Okay, so you can imagine that there are a lot of matrix norms. Pero ang madaling makita ng mga matrix norms ay yung mga matrix norms na induced or generated or ano pa bang ibang term? Or yung nanggagaling dun sa mga vector norms, right? So, tatawagin natin sila mga natural norms o mga operator norms induced by vector norms. Sila yung nasa definition 8.4. It says na kapag ka meron kang isang vector norm, okay, sa set of n by 1 matrices, because n by 1 matrices are what we consider to be vectors, okay? Now, kapag ka, pwede kang mag-define ng isang function from the set of n by n matrices papunta kay R in such, in the following way. I-assign mo to the function value of a matrix A yung supremum, all right, ng ano, nung matrix times a vector, tapos ito ay n by n, ito ay n by 1. So the product makes sense. The product will be n by 1. So isa siyang vector, kaya yung measure ng ax is taken as a vector norm. Okay? Computein mo yung vector norm ng product na ax, i-divide mo siya sa norm ni x, tapos kunin mo yung supremum ng lahat ng ratios na to over all vectors na non-zero yung norm. Okay? Or essentially, that will be taking the supremum of this quotient over all non-zero vectors. Okay? Yung supremum na yon, yun yung i-assign natin to be the measure for the matrix A. And we call that measure for the matrix A natural norm or an operator norm induced by a vector norm. So kung meron ka ng measure para sa isang vector, all right? Para sa isang vector space, pwede mong tingnan, pwede mong sukatin yung magnitude ng matrix A by looking at its action on the vector space. So si A, ita-transform niya yung vector X into another vector, let's call that vector AX. Tapos tingnan natin gaano kalaki yung AX. I-divide ko siya, parang percentage error to, doon sa parang percentage difference to, all right? So, i-divide mo siya by the magnitude of the vector x. Tapos kung ano yung least upper bound ng mga ratios na to, yun yung i-assign natin to the measure of A. And by remark 8.4, we are guaranteed that an operator norm induced by any vector norm ay laging matrix norm. So lahat ng norms, lahat ng functions na i-define mo this way ay mga matrix norms. I know it's quite difficult to imagine it or to see how this is computed kasi nga medyo shook tayo dyan kasi may supremum. Sir, bakit 155 yan meron sa 174? Meron sa 175. Ganun talaga nagko-crossover yan. But essentially, bibigyan ko naman kayo ng shortcut kung paano ko computein yung mga vector, yung mga operator norms na yan, right? So ito lang yung theoretical way on how to do it for arbitrary vector norms. Pero sa 1 norm, sa 2 norm, at saka sa infinity norm, ibibigay ko na yung shortcut paano sila ma-compute. And I hope you will accept this even without proofs. All right? Ipapresent ko na lang yung calculations. Paniwalaan nyo na lang ako this time, guys. All right? Hindi, wala akong time para i-prove sila. Okay? So usually, pinoprove siya sa linear algebra or sa functional analysis. So, kaya hindi na natin siya gagawin sa 175. Excuse me, guys. All right. Going back. Now, merong isang magandang property yung operator norms kung bakit sila yung usually pinipili. Alright? Kasi yung mga matrix norm, vector norms din naman yan. Kasi sabi ko nga, ang set of all matrices ay vector spaces din. So, ibig sabihin yung pag operator norm ka, pwede kang tingnan din also as a vector norm. Okay? Ang maganda sa kanya ay meron siyang consistency property. Ano yung consistency property na yon? Yung magnitude na to, yung operator norm ay laging mas malaki kaysa dun sa ratio ng vector norms ng norm ng ax at saka ng x. It's straightforward from the definition because we said that the operator norm is just the supremum or the least upper bound of these guys. So lahat ng ratio na ganito yung itsura is always bounded above by the operator norm. And then if we multiply both sides by the norm of x, we get this inequality. All right? So ibig sabihin, kapag ka si A nag-operate siya kay vector x, yung laki ng vector ax ay hindi lalaki or hindi lalampas dun sa dun sa norm ni vector x times the operator norm. So ibig sabihin hindi masyadong nagbo-blow up yung norm ng ax compared to the norm of x, right? Kasi hindi nga siya lumalampas sa size nito. Kasi ayaw natin na yung isang maliit na vector x ay magkakaroon ng super laking magnitude after transformation by the matrix A. Though I don't want to go there into a more detailed explanation on that kasi pang linear algebra siya. So let's just bear this in mind na yung action ng isang matrix A ay hindi masyadong pinapalaki yung yung uh, yung size ng ng vector x because the size of the image of a vector x after transformation by a matrix A ay hindi lumalampas dun sa operator norm ni A times the size of the vector x. So laging meron kang consistency property bounding the norm of the result of the operation and by the multiple or by a multiple of the size of the input. Okay? And then as promised, ito yung mga simple formulas para sa mga common p-norms. Okay? So in general, ganito natin dapat ko-computein yung p-norm. Okay? Ng isang matrix. So you get the supremum ng p-norm ng vector ax divided by the p-norm of the vector x. And then the supremum is to be taken all over all non-zero vectors. Okay? Pero may equivalent definition kasi yan. Instead of taking the supremum of this guy over all non-zero vectors, it can be shown that the same value can be computed by simply looking at the supremum of the p-norms of the vectors ax, where x is over all vectors with unit norm. So hindi mo na pala kailangan kunin yung ratio. Another way of computing it, kunin mo na lang yung supremum ng norm ng ax over lahat ng x na may norm na equal kay 1. Okay? And with this definition, I think it's easy to find that the one norm of a matrix A is simply this guy. So, ito ay na-derive mula sa definition na to. Alright? So essentially, if I ask you to compute the one norm of a matrix A, you just need to get the maximum of this summation. Okay? And what is this? This is the absolute column sum. Right? Kasi kukunin mo tong sum pero fixed dito si J. So kukunin mo yung absolute value ng lahat ng laman ng matrices mo. Tapos, kukunin mo yung summation na starting from 1 to n. So, pero fix si j. So, fix si j, right? So, halimbawa, meron tayo dyang matrix. Fix si j, tapos ang I going from 1 to n. So, kukunin ko tong sum na to. Ito yung corresponding para kay j equals 1, kasi first column. Tapos, ito yung corresponding para kay j equals 2. Ito yung corresponding para kay j equals 3, and so on. Alright? Tapos, fix si j, we're taking the maximum over all j's starting from 1 to n. So, ibig sabihin, kukunin ko yung pinakamalaking column sum. Actually, not just the column sum, pero yung pinakamalaking absolute column sum. Kunin yung absolute value ng lahat ng entries, kunin niyo yung sum sa bawat columns, yung pinakamalaking column sum, yun yung one norm ng matrix A. I see somebody raised their hand earlier. May questions ba?
Sir, wala naman po. Hindi lang po kasi nag-load agad yung drawing niyo.
Thank you, thank you. Yeah, napansin ko rin yung kaya lang, baka sa internet ko lang, sa lahat pala, sorry. So, I mean, internet ng laptop ko, hindi pala. So, sa connection pala nung iPad ko. But anyway, so yun yung one norm. So, hindi nyo na kailangan gamitin tong supremum. So, hindi nyo na kailangan mag-review ng 155 para lang makompute yung one norm. Okay? So, ito na, yung formula para sa one norm. Tapos, pagka pinag-isipan mo rin, ginamit mo yung definition, kinuha mo naman yung infinity norm, equal naman siya dito. Ang infinity norm ng isang matrix A ay maximum lamang ng summation na to. But essentially dito, fixed naman si I. So, kukompute natin tong summation na to sa lahat ng I going from 1 to n. So, ito yung I equals 1, I equals 2, I equals 3, alright? Kasi yung I, lagi natin yan yung row counter. Tapos, kukunin ko yung summation sa bawat isang I na to starting from j to 1 to, from 1 to n. So, ibig sabihin, isa-sum ko yung absolute value ng mga entries sa bawat row. Tapos, sila yung candidates para maging infinity norm. Alright? Then, I'll get the maximum among those absolute row sums, and that will be assigned to be the infinity norm of the matrix A. Okay? So, yan yung i-assign natin as the infinity measure ng isang matrix A. Now, medyo mahirap yung 2 norm. Alright? Pagko-compute ng 2 norm. Let's just accept, kasi sa linear algebra nga ito kino-compute. Ang 2 norm ng isang matrix A ay equal sa square root ng kanyang spectral radius. Si row of A, siya yung tinatawag natin na, ayun pala, spectral radius ni A. Kunin mo yung square root ng spectral radius, yun yung 2 norm. That's why usually the 2 norm is also called the spectral norm. Okay? Kasi siya yung square root ng spectral radius. What is the spectral radius ng isang matrix? The spectral radius of a matrix A, which is denoted by row of A, ito yung pinakamalaking eigenvalue ng A transpose A. Okay? But I hope you guys have an idea how to compute eigenvalues already. So, oh yeah, but let me check this one, right? Hindi, tama to. Ito yung definition. Siya ay largest eigenvalue ng A transpose A. Yun yung spectral radius. Alright? So, kailangan mong computein yung mga eigenvalues ng A transpose A. Yun yung spectral radius. Kunin mo yung square root nun, yun yung 2 norm. Medyo matrabaho yung 2 norm. Alright? Pero syempre, gagamitin lang natin si MATLAB o si Python para sa kanila. Actually, mas madali yan para sa atin. Halimbawa kay MATLAB, ang syntax lang ay norm. Tapos, mag-i-input ka lang dyan, either a matrix or a vector, comma P. Ibibigay niya na kagad yung P norm. Alright, so take note of this syntax, especially for MATLAB users, right? So, lagay mo lang dito, kahit vector yan, kahit matrix yan, pa-compute mo yung norm, pwede kang maglagay kung anong klaseng norm yung gusto mo. Is it the 1 norm, the 2 norm, the 3 norm, the 4 norm? Pwede nga rin ditong infinity norm. Lalagay mo lang I and F kay MATLAB, it will give you the infinity norm. So to compute this guy, lagyan mo lang to ng comma 2. Alright? Para makuha yung spectral norm ng isang matrix A. Now, hindi lahat ng mga matrix norms ay nanggagaling sa vector norm. So, ito mga pinakilala ko sa inyo, lagi silang induced by a vector norm, right? So, merong mga matrix norms na hindi nanggagaling sa vector norms, such as what we call the Frobenius norm. Yung Frobenius norm ng isang matrix ay equal sa square root ng trace ng A transpose A. I don't know if you guys are familiar with the trace, pero the trace is just the sum of the diagonal entries. So, computein mo yung A transpose A, multiply mo lang naman yung transpose ng matrix dun sa matrix A, may makukuha kang matrix, kunin mo yung sum ng diagonal entries, yung sum ng diagonal entries, yun yung tinatawag nating trace. Kunin mo yung square root ng trace, yun yung Frobenius norm. Okay? So that's another type of matrix norm. Okay, so to illustrate, dahil wala na akong oras, kindly go over example 8.5. So paki-verify yung mga numbers na nandyan. Okay? So meron akong matrix na ito yung laman. Alright? Tapos kukunin ko yung one norm. Ang one norm niya ay 18 because ano nga ang one norm? Absolute column sum. So absolute column sum, 1 plus 8, 9. And then 9 plus absolute value of negative 9, that's 18. The infinity norm is the maximum absolute row sum. So it will give us 17. All right? Yung 2 norm, medyo tricky. Kinompute ko siya symbolically. Ito yung sagot. But that's approximately 13.8927. Okay? But you can do this in MATLAB. Gawin nyo lang norm ng A, comma 2. That will give you the 2 norm of that matrix A. Don't worry, hindi ko naman kayo pagko-computein mano-mano. So ipapa-MATLAB natin yan. Tapos ang Frobenius norm niya ay 15.0665 because first I need to compute A transpose A. Pinag-multiply ko lang yung matrix saka yung transpose niya. Kinompute ko yung transpose. Ang transpose ay sum ng diagonals. But here, sum siya talaga ng diagonal entries, hindi sum ng absolute values. In this case, positive sila parehas. So 65 plus 162, you get 227. Take the square root of 227, that's going to be the Frobenius norm. Okay. Now, ito yung mga ways to measure a matrix or a vector. And as I mentioned earlier, measuring vectors will be important because this will be involved in the stopping criterion for our iterative methods. Kasi ang kinukuha natin ay gaano kalaki yung pagbabago dun sa ating estimate and measure if that is enough within some threshold that we will set. Okay. Now, yung matrix norms naman, importante sila kasi sila yung magbibigay sa atin ng idea kung nagko-converge ba yung iterative methods natin. Okay? So I think we're ready to start talking about the iterative methods. Pero do you guys have some questions bago tayo magpatuloy? Sorry, naging crash course siya sa linear algebra, kasi yun yung problema ko sa 175 eh. Lalo na yung chapter 2 and 3. May mga topics na nanggagaling sa ibang courses na hindi naman prerequisite sa 175. So kailangan ko talaga siyang i-discuss at least on an introductory level. Okay? So questions? Siguro nung umpisa kinakabahan kayo, no? Pero nung nakita nyo na, may syntax naman pala yan kay MATLAB. So okay na yan, sir. Kayang-kaya namin yung i-type, at least for now. All right. Okay, thank you, Ezekiel and David, for your validation done. So let me borrow siguro 5 more minutes. Let's end at 12:55. Okay. Habang nag-absorb pa si Charles. Ganun naman talaga yan, na kahit anong mathematical idea, hindi natin yan nakukuha sa isang upuan. So it needs to ferment. Ferment ba? Ferment. Basta one of those two, guys. Kahit nga sa mga conferences, pag-attend ka ng conference, feeling mo, sa umpisa, lalo na sa mga estudyante, pag nakinig ka ng seminar, ng webinar, o ng conference, isipin mo parang wala naman ako naintindihan. Ganun ba ako hindi kagaling? Na wala ako naintindihan dun sa sinasabi ng speaker. Don't worry kasi kahit mga professional mathematicians usually, nakaka-experience ng ganun. Actually, pumupunta lang kami sa mga conferences para sa libreng kape, libreng tinapay, libreng lunch, ano. Pero usually hindi mo talaga makukuha yung hindi mo makukuha yung gist ng isang seminar, especially kung hindi yun mismo yung specialization o yung ginagawa mo, alright? So, magkakaroon ka lang ng snippets, small ideas. Sabi nga sa isang presentation, off topic na naman, pero share ko lang, ang dapat maintindihan mo sa isang 15-minute talk, siguro yung introduction, the first 2 to 3 minutes. Kasi magkakaroon ka ng idea ano yung problem, ano yung ginagawa ng taong ito. Tapos yung conclusion, yung last 2 minutes. Tapos kung ikaw yung speaker, dapat wala nang maintindihan yung audience dun sa gitna. Kasi kung naiintindihan pa ng lahat, ibig sabihin napaka-trivial ng ginawa mo or something like that, right? That's a half joke, but I think that still applies. So wag kayong masyadong discourage kung it takes time for you to absorb a certain mathematical idea, because that happens even to the best minds. All right. Okay. So pahapyawan ko yung iterative methods, ano yung idea behind it, and we'll talk about the Jacobi method starting next meeting na lang. So yung tatlo, pagkakasyahin ko siya in one meeting. Paano natin i-design yung iterative methods? So ito ay parang kahalintulad lamang ng isang fixed point iteration. Pero mas malaking level kasi matrices and vectors yung involved. So kung given tayo ng system AX equals B, equivalent yon, of course, sa isang root finding problem. So subtract b from both sides, we get this guy. Ax minus b equals the zero vector. Okay? Now, root finding siya. Hanapin mo yung root x ng linear vector function ax minus b. Right? Tapos ang strategy natin ay i-translate itong 8.1 into a fixed point iteration. X equals tx plus c. We want that the fixed points of tx plus c, all right, where t is a vector, where t is a matrix, we call t the iteration matrix. This would be n by n. Our vector x is n by 1. The vector c is n by 1. Okay. T and x will be T and c will be determined later, and they will be determined typo. They will be determined so that yung roots ng equation na to ay equal dun sa fixed point x ni tx plus c. So ibig sabihin yung solution ng fixed point equation 8.2 dapat ay equal dun sa roots ng equation 8.1. Ganun na natin hanapin yung t. Pero ang kagandahan sa form na to, bakit natin siya ita-translate into a fixed point problem? Kasi marunong na tayo mag-fixed point iteration. All right? So what we'll just do is to define a computation scheme or an iteration scheme that looks like this. Yung k plus 1 estimate, which is a vector. So gumamit ako dito ng superscripts kasi usually yung subscript ginagamit natin para sa laman ng isang vector. So yung x upper k plus 1, which is our k plus 1 estimate, will be equal to the iteration matrix times the previous estimate plus the constant vector c. Kaya ang tawag natin kay t ay iteration matrix kasi siya yung nagbibigay sa atin nung uh, nung bagong estimate. All right? Or basically, nandun din si C, pero essentially, we just scale our previous estimate and then translate it by a vector C to get our k plus 1 estimate. And of course, here we need some initial condition. Right? So meron mga ilang bagay tayong dapat tingnan dito. Una, paano ko ita-translate yung ax equals b into a fixed point problem x equals tx plus c. Right? Tapos pangalawa, okay, pag na-translate ko na siya for some, using some techniques, paano ko mag-guarantee na itong iteration na to ay magko-converge? Kasi yun yung problema natin. Hindi porket meron kang fixed point iteration, magko-converge na siya palagi. And I think last time we had the contraction mapping theorem that tells us kailan nagko-converge ang isang fixed point iteration. So kailangan nating i-guarantee dapat magko-converge itong iteration na to. At kung magko-converge ba siya, actually even before convergence, unique ba yung solution ng fixed point iteration? Kasi baka naman, tinranslate mo yung solution mo ng system na to which has a unique solution. Kung si A ay non-singular, kinonvert natin siya sa isang fixed point iteration na baka naman ito napakaraming solutions. So we also need to guarantee that the fixed point iteration that we design will have a unique solution and the iteration scheme will converge. Ano yung kailangan ko para sa iteration matrix T para mag-converge itong fixed point iteration na to? Pangatlong tanong, okay, kung posible siyang mag-converge, ano yung condition dun sa initial guess? Alright? Kasi remember Newton-Raphson, kailangan merong certain criteria kung kailan magko-converge si Newton-Raphson. Ano dapat sabi natin noon, dapat malapit yung x sub 0 dun sa actual solution. Now, in our case, what would be the requirement for x upper 0, the initial guess? And this is quite difficult. This is more difficult kesa dun sa kaso natin sa root finding techniques. Kasi sa root finding technique, pwede nating ipag-graph yung function. Pag pinag-graph mo yung function, magkakaroon ka ng idea saan malapit yung root. Alright? Tapos, edi yun yung gawin mong initial guess. Alright? So, there is a bigger chance of getting a nice initial guess. But for linear systems, especially for large ones, halimbawa 1,000 by 1,000, yung linear system mo, there are 1,000 variables to be solved. Then, we cannot easily get a good idea for an initial guess. Alright? Kaya, mas gusto natin na sana etong iteration na to magkaroon ng napaka-loose na requirement kay x upper 0. And then, susunod na tanong, hindi ko na alam kung ilan na yung natanong ko, yung susunod na tanong ay gaano kabilis yung convergence. Alright? So, sa root finding, ang mga fixed point iterations, alam natin to converge linearly na napakabagal naman. Ano? At yun ay isa ring malaking problema para sa linear systems kasi usually computationally expensive itong pagko-compute ng linear systems. Actually, hindi pala siya gaanong computationally expensive. Expensive siya insofar as memory is concerned. So kung meron kang isang malaking matrix, isasalpak mo siya sa laptop mo, magrereklamo sa laptop mo na hindi na siya kakasya. I don't know if you guys already encountered it. Na-amazed lang ako. Meron ako sinosolve na linear system. Pinagawa ko siya sa computer ko. Mayabang ako. Sabi ko, kaya yan ng computer ko. Gumastos ako siya ng malaki. Pero nung in-input ko yung matrix dun sa computer ko, nagreklamo na siya. Sabi niya ay, yung matrix mo, ang size ay, ganun ang kalaki yun? Ang matrix ko ay parang 12 gig yung laki niya. Imagine, a bunch of numbers na 12 gig yung laman, ilang high def movie na yon, no? So, ganun kalaki yung matrix, ang RAM ko lang yata ay 16 gig or 32 gig. So, nagreklamo na siya kasi mag-run pa yung OS and so on. So, sabi ni MATLAB, hold on, hindi ako papayagan ng laptop mo na gamitin yung 12 gig para i-store etong matrix A na to. Tapos yung matrix A na yon, hindi ko lang siya i-store, ipang-ooperate ko pa siya. So at any given point in time, there would be more than 12 gigabytes of storage required para dun sa operation ko. Kasi 12 gig yung matrix, syempre yung result ng matrix, ilalagay niya pa sa random access memory and so on, so magkakaroon ako ng isang problema. So, isa siyang malaking storage problem, so we want us to be done with the calculations as fast as possible. Okay? So yun yung mga titingnan nating mga tanong as we design a fixed point iteration next time. Pangarap lang pala yung masimulan ko yung Jacobi, ano. Pero yeah, let's see. Next time, I'll teach you how to get the iteration matrix, okay, para dun sa Jacobi method. And then we will observe how fast the convergence of the Jacobi method is. Makikita natin mabagal siya. Dahil mabagal siya, of course, numerical analyst tayo, hanap tayo ng paano siya mapapabilis. And the answers are the Gauss-Seidel method and the successive over-relaxation or the SOR method. Okay? So I think that's it. Sorry for taking up 6 more minutes, but I hope you guys are fine with that. Talagang in-expect ko matatapos ko yung Jacobi today. But anyway, and that's the problem kasi may preliminary na linear algebra kung kailangang i-discuss. Ayoko naman na ibigay lang sa inyo yung syntax na norm comma something that you won't have any idea how it worked na mag-ano lang tayo, magre-rely sa machines. And I think that's one problem now, especially sa data science. Masyado tayo nagre-rely sa black boxes. So bilang mga mathematicians tayo yung nagde-design ng black boxes nung mga parang mga machines na ginagamit ng ibang applied scientists na maglalagay lang sila ng data tapos magbibigay yung black box ng output. Pero hindi tayo pwedeng ganoon. Kasi tayo yung nagde-design ng black box na gagamitin ng mga applied scientists. So dapat alam natin paano naki-carry out yung process at least on a conceptual level para magkaroon tayo ng idea how to design these methods. Okay? So I hope you get the point. So and then you got something new from today. Kahit na vector norms saka matrix norms lang yung napag-usapan natin. Malamang alam niyo na siya kung nag-matrix algebra na kayo. All right. So yeah, but promise on Friday you'll get something new. We'll talk about Jacobi, Gauss-Seidel, and successive over relaxation method. Babawasan ko na yung chismis para matapos natin siya. All right. So and then the lab exer for Monday will be available siguro pag natapos sa susunod na update nung module 8. All right. So which will be madaling araw na ng Friday. Okay. So, any questions, guys? Okay, kung wala na mga pahabol, I let you go na. Let's see each other again on Friday. Bye, guys.